Around this time of the year, I start to daydream about the beach. I start to think about the sun shining down on me and kicking back with a good book, and, getting my feet wet, and feeling the sand. But I always have two main issues with the beach. First thing I want to do is kick off my sandals and just start running in. But immediately the sand is just way too hot. It's not even like reasonably hot. It's like burning, scorching hot. So that's an issue. So I either got to put my flip-flops back on, or I got to go stand on a towel, or I run for the ocean. Well, if I run for the water, I get my feet in there, it's like freezing. It's super cold. So this is not only troubling, in a physical standpoint, but also in an academic one. It gets me thinking. If both the ocean and the sand are receiving sunlight, and they're essentially receiving the same amount, why do we have so much of a temperature difference between the sand on the beach and the ocean water at the shore? Well, part of it has to do with the specific heat capacity of those two substances. So let's talk about what that means. The specific heat capacity is, by definition, a measure of how much heat needs to be added or removed to change the temperature of 1 gram of a substance by 1 degree Celsius. Well, that's kind of stuffy. If we kind of break that down a little bit, that's just a fancy way of saying, how difficult is it to change something's temperature? How much heat is it going to take before your thermometer starts budging? In general, the higher the specific heat capacity is, that means the harder the temperature is to change. Okay, it takes kind of more heat for our temperature to start moving. For a lower specific heat capacity, it's easier to change the temperature. So we just put in a little bit of heat and it starts flying away from us. We can look at specific heat capacity in two major ways, either by graphing it out or by just having a bit of data. So let's look at the graphing first. So on a graph, something like this down in the bottom right, we tend to put heat on our y-axis and temperature on our x-axis, or at least that's how I like to visualize it. And I make a lot of comparisons to how we graph density here. When we graph density, we do mass per volume. So we'd have mass going this way and volume going this way. So the more mass you can squeeze into a certain amount of volume, the more dense that substance is going to be, the steeper your slope is. And the slope of that line is rise over run, which is mass over volume. So that is the density. The slope is the density. In this case, we're making a graph that has heat versus volume to say how much heat does it take for our temperature to change by how much. So the steeper the slope is, that means the more heat I have to put in before my temperature starts changing, which implies a higher specific heat capacity. Whereas if I only have to put in a little bit of heat before my temperature takes off and I have this kind of flatter slope, that means I've got a lower specific heat capacity. It's easier to change the temperature. When we do a graph like this, we're kind of making an assumption that this is for 1 gram of something. That something could be water, oil, sand, glass, ceramic, graphite, hydrogen gas, doesn't really matter. As long as we're showing how much heat it takes on the y-axis, okay, to get a certain temperature change on the x-axis. So our rise over run for 1 gram of that stuff is going to be the specific heat capacity. All right? Again, to summarize, a higher specific heat capacity means it's harder to change the temperature. So we would see that as a higher, steeper slope where we have to put in more heat on the y-axis to get some temperature change on the x-axis. A lower specific heat capacity means it's easier to change the temperature of something, which we see in a lower, flatter slope where you only put in a little bit of heat and then our temperature is flying away from us. Okay? Graphing is just one way we can show this. We can also see this just in the value, just like we can do with the density. I can calculate the density of a substance to be some number in grams per milliliter. We can do something similar with this. Okay? Rather than doing mass per volume, we're doing heat per temperature. So, when we look at this in terms of data, that value of the specific heat capacity, the number, shows us how much heat it takes to change that temperature, 1 degree Celsius, essentially at a time, okay, for 1 gram of something. If we have more than 1 gram of something, it takes, of course, more heat, but it follows this kind of ratio. Okay, so a higher specific heat capacity is shown in a higher, larger value number. So 3.2 might not be a big number for us, in our day-to-day lives, but it's actually a pretty big number for the specific heat capacity. Our units also look a little bit crazy, but we can kind of break this down. Specific heat capacity should be how much heat it takes for some amount of mass to be cranked up to a certain temperature. Well, our heat is measured in joules. That's also generally used for energy in science. Okay, big J is for joules, Joules. The G is for grams. That's our mass. How much stuff are we trying to heat up? Okay, and this degree Celsius is how much is the temperature actually increasing. For some substances, you put in a little bit of energy in terms of joules, and you get a big temperature change. Sometimes you have to put in a lot of heat in joules to get just a small temperature change in degrees Celsius. Okay, and again, the mass affects that too. So this unit reads joules per gram degree Celsius. Okay, but since we're just going to be kind of comparing one specific heat capacity to another, and we're not going to do a calculation with this for now, it actually is a little bit easier. We can kind of ignore this unit. Okay, it's good to know why it looks like this, but it's going to look like this for any specific heat capacity, no matter what substance you're looking at. Okay, if we look at a lower specific heat capacity, where it's easier to change the temperature, that means we've got a lower, smaller value number, like 0.7. Okay, or 0.5 or 0.1. These numbers get pretty small for materials that heat up very easily and get hot very easily with just a little bit of heat added. Okay, so we can look at a couple examples of this on a graph and with data. Okay, talking about the beach, here's our sand versus water example. So on this graph here, the light gray line is my ocean water, and the kind of dark gray line is my beach sand. Well, this is heat in joules on the y-axis and temperature in degrees Celsius on the x-axis. I can see that both of these change by the same amount of temperature. They both go from 5 degrees Celsius to 20 degrees Celsius. So they're both making the same temperature change. But it takes a different amount of heat to do so. Okay? For my sand, I'm just bumping up a little bit, and then all of a sudden, my temperature increases way fast. For the water, I've got to crank in all this heat. Okay, that's like from 20 to 60, or 20 to 80, that's like 60 joules. Okay, and then I get that same temperature change that we got from just like not even 20 joules for the sand. Okay, so way less heat goes in for the sand, and we get the same temperature change as way more energy put in for the water. We can see this also not just by the higher slope, meaning a higher specific heat capacity for water, but also this higher number down here. Water has a specific heat capacity of 4.184 joules per gram degree Celsius, which again doesn't look like a big number for us, but that's pretty huge for a specific heat capacity. It's kind of one of the ones that sticks out as like, wow, this is a really high specific heat capacity. Sand, on the other hand, has a heat capacity of 0.8 joules per gram degree Celsius. So much smaller number. So it's a lot easier for that temperature to change as we add in heat. Okay. Just as a note, this also goes for removing heat. Same way. It's just that your temperature would drop instead of increase. But usually it's just easier to talk about in one direction. So we talk about heating rather than cooling off. But it works the same way. Let's look at another example. Okay? Mercury and ethanol are both substances you can use in a thermometer, but they have different specific heat capacities, which could affect the choice that you make and what thermometer you use. Now, there are lots of reasons why you might pick one thermometer over another, which could be cost reasons or it could be safety reasons. So mercury might be giving you a more accurate reading, but at the same time, it's a little bit more dangerous if it breaks and it escapes the thermometer. Versus ethanol, which is a little bit cheaper, not so bad if it gets out. Okay, we can also compare their specific heat capacities. Ethanol is our light gray line here, and we have to put in a whole lot of heat just to get our temperature to change, kind of like the water. But our mercury, we barely have to put in any heat at all, and boom, our temperature flies up. So this lower, flatter slope indicates a low specific heat capacity, easy to change the temperature, whereas this higher, steeper slope indicates a higher specific heat capacity. It's harder to change the temperature of ethanol than it is for mercury. We can also compare their data. The specific heat capacity of mercury is 0.14 joules per gram degree Celsius, whereas ethanol's is 2.4 joules per gram degree Celsius. Okay, so again, smaller number, smaller specific heat capacity, easier to change the temperature. Larger number, larger specific heat capacity, harder to change the temperature. Okay, so a mercury thermometer might be a little more expensive and a little more dangerous to handle the materials inside if it breaks, but it doesn't take as much heat for our temperature to start changing, which causes the liquid inside to expand. So you can think of it like, maybe mercury works a little bit faster than your ethanol thermometer. Maybe you don't have to hold it in your substances long. So kind of interesting. You might also be able to expand the liquid up into a greater volume, which means you can reach higher temperatures on a single thermometer rather than trying to push your ethanol thermometer to its limits just to get to maybe 120 degrees Celsius. We're looking at one more example here, comparing wood and rubber. Say you're buying a pot, to cook pasta in or soup or something like that. You might look at having a wood handle versus a rubber handle for a lot of different reasons, including aesthetics, how you want your cookware to look. But if you're worried about having to wear special gloves or something, or having a pot holder, and that's not kind of your thing, then maybe you should look at how those two different materials conduct heat and how quickly they change temperature as they receive the same amount of heat. So this is comparing wood and rubber's specific heat capacities. We want a pot to conduct heat well and for it to heat up quickly so the food inside gets hot quickly. But we don't want that to happen to the handle, because that's kind of where our hand is going to be. We don't want to burn our hand. So if we compare the wood to the rubber, it's pretty close. But our rubber just barely has a higher slope, a steeper slope, which means it's got a higher specific heat capacity. On the other hand, our wood has a lower specific heat capacity, which means it heats up and increases in temperature a little bit easier. Okay. Now, in the case of the handle, again, we don't want it to heat up. We don't want it to get hot. So rubber would probably be a better choice, but you might choose the wood because it looks nicer. We can see this in their numbers too. Again, pretty darn close. Okay, so I wouldn't use this as your final decision-making process to pick what cookware you get, but it might kind of nudge you in one direction or the other. So rubber is going to be a little bit harder to warm up than a wood handle would be. Okay, so that's specific heat capacity. Whether you're looking at a graph or looking at the data, a higher specific heat capacity implies that it is harder to change the temperature. Okay, so as we continue to add heat in, the temperature doesn't increase as much. As you remove heat, it doesn't decrease as much. And for smaller specific heat capacities, lower specific heat capacities, it's easier to change the temperature. Adding heat or removing heat causes a much greater temperature change in those cases.